Ya. Muy buenos días. Gracias por asistir a esta presentación, en la cual vamos a presentar a un investigador que nos está visitando. Ellos tienen, es una delegación, en este caso, de dos personas que vienen de China, de Beijing. Son investigadores de los observatorios nacionales de China. Tienen diversos trabajos, entre ellos los más importantes los desarrollan en la Antártica. Con nosotros, ellos tienen un proyecto de investigación, el cual está en ejecución, que nos ha permitido tanto formar capital humano, en este caso un compañero de ustedes, hizo su tesis con ellos y logramos ir a la base de China para evaluar más colaboraciones en el futuro. Actualmente están aquí hablando con todos nosotros, los profesores del área de señales y telecomunicaciones, para ver qué proyectos podemos seguir sacando para los próximos años. ¿Ya? En cuanto al expositor, tengo el torpedo aquí apagado. Ya. En cuanto al expositor, les voy a presentar en este caso al doctor Chan. Él sacó su doctorado en la Universidad de Texas, en Austin. Hizo su postdoc en la Universidad de Wyoming y actualmente es profesor en la Tianjin, fue profesor desde 2006 a 2018 en la Tianjin University y actualmente es investigador de los observatorios nacionales de China. Okay? Thank you so much, Professor Chan. You could start the presentation. Thank you.
Good morning. Very happy to be here to talk to you about our work in Antarctica. So you'll receive this slide. So what brought us here is actually the STAR conference. That's that one. So it's Open Science Conference for the STAR Scientific Committee of Antarctica Research at Pucon. So we took this chance to also visit here. But what brought us here, as you can see, is actually this part. So we have a collaborating project with Professor Henry and Professor Bustos. So it's involving my institute, UCSC and UCN. So we're developing an instrument to do the site testing for astronomy observations. That's at several Venezuelas close to Antofagasta in the north. So all the instruments will be automatic and unattended. So that part is related to what we have done in Antarctica. So I'm not going to talk about this instrument today. So what I really want to talk to you is about our work in Antarctica. So the first question is, why do we want to do astronomy in Antarctica? So this map shows the current best observatories in the world. So one's in Hawaii, another observatories are in the northern Chile. I guess all of you probably know this, know that. The biggest telescopes are building right in northern Chile. There's another one in south of Spain. So when we do astronomy, we always want to have a dark sky so we can see the stars clearly. So, and in Antarctica, there's also another advantage because it has polar nights. So the night can be 24 hours long. So we can observe stars continuously. So the second advantage is because Antarctica is very cold. The good thing for that is when we do astronomy, we do not only look at the stars with our eyes, with naked eyes, that's the visible light. We also want to do that in the other bands, infrared, microwave, X-ray, so everything. In infrared, we also want a very dark sky. But in infrared, the dark sky needs very cold environment. And that's why Antarctica is good for infrared. So it's very cold and the sky in infrared is very dark. So this is for another reason. The third one is similar to the infrared part, but in a different band. So here I listed all the wavelengths, all the electromagnetic spectrum we need to observe in astronomy. So in these two bands, this is visible, this is radio. So we can receive the signal from the stars on the ground, but all the other bands, the atmosphere blocks them. So they do not get down to the ground. So we have to use a satellite or even a plane to get above the atmosphere so we can receive those signals. But the good thing for one band is it's called a sub-millimeter or terahertz. That signal is blocked by the water vapor in the atmosphere. So if there's no water in the atmosphere, then the signal can get down to the ground. And that's why it's good in Antarctica, because in Antarctica, it's not just very cold, and it's also very extremely dry. So there's a very minimal water vapor in the atmosphere. So in that band, the signal can get down to the ground, and we do not have to send a satellite to observe that. We can do that on the ground. So that's this sub-millimeter band. And also the air is very clear, it's very clean. So this picture, I took this picture, and this is a very thin bamboo stick. So if I move a little bit, I can block the sun just with this very narrow, very thin stick. So, and there's no scatter light around the sun. So the sky here in Chile is already very clean, but sometimes you still see it's blurred and there are lights around the sun if you look at that. But in Antarctica, it's so clean, you can just block the sun without any scatter light. That means the atmosphere is very clean. There's no dust, there's no aerosol. So that's a good thing. But more importantly, the atmosphere is also very stable. That's one of the most important thing we want in astronomy. There's a term called thin. What it really means is whether the star is twinkling or not. So when we want to take a good picture, we want the star to be not to twinkle, to be very stable. So we call that a good thing. So when the thing is bad, it's like this. You take a picture, it's blurred. So we want to find places with a very stable atmosphere and a very good thing. So the atmosphere in Antarctica is very stable. So we also want to find a place to do the astronomy in Antarctica. That's another reason. So basically a short summary here. So why do we want to do astronomy in Antarctica? Because it's not everywhere. It's called Dome, that place. It potentially has the best observing conditions for astronomy on the ground. And we have done a lot of work. I believe we have removed this word. We have proved it does have the best observing conditions for astronomy on the ground. So I will show you our results. So where is Dome? So this is Chile. So this is Antarctica. So if you look at this map, Antarctica is very big, but we are going very deep inside Antarctica to get to Dome. It's the highest place on the ice cap, and the altitude is very high. It's more than 4,000 meters. So before 2004, 2005, nobody has been there. Nobody has been there. So that's the first time when people can drive from the coast to Dome. And this is a different view, but this is not to the scale because the mountain here is only like 1,000 meters, and the ice is like 3,000 meters thick. Okay, since then we set up an observatory and put a lot of instruments, both astronomy observations and the site testing. So this is our first telescope. It's very small. It's only this tall, with 14 centimeter size telescope, small telescope. Four of them. We'll put them in like an array. So we call that a Chinese small telescope array. But it's very small, but it has a very big field of view. So if you take one picture, it can host like 80 full moons. It's very big. What it does are two things. One is to observe the stars repeatedly, so we can see the star changes. So the brightness of the stars changes. These are three examples. Another thing is for site testing. We want to know how good the site is at Dome for astronomy. So a few years after that, we set up another site for astronomy. And now we have bigger telescopes. So these telescopes have a larger aperture, half meter, 50 centimeter wide, and like 4 meters tall. We call that an Antarctica survey telescope. So these are real telescopes. They can point to anywhere we want to look at. So the main purpose for this one is called the time domain astronomy, to do the time domain astronomy. What that means is they observe the objects, the stars, which are changing. So everything basically is changing. So we observe the stars over and over and look at how they are changing, how the brightness are changed. So this is one example. So we can do a lot of things like supernovae, gamma ray bursts, exoplanets, gravitational wave objects. So this is an example for the exoplanets. So how do we find exoplanet? So if you have a planet around a star, if it goes like that way, when we look at it, so some of the light will be blocked. A tiny part of that will be blocked. So if you observe this pattern, you know that there's possibly there is a planet around that star. This looks very easy, but it's hard because this change is very small. It's only 1% or less, like 0.1% maybe. So we use this telescope to do this science, to do this observation. And they did find many candidates. So you see that signature, that pattern. So just like what we showed in the previous slide. So they found out a lot of candidates, more than 100, but they need to confirm that with spectroscopy, with more observations. Okay, so for all those telescopes, they have to be operated automatically and mainly unattended, because at that site, at Dome, there's nobody in the winter. We can only go in summer. Then after we leave, there's nobody there. So all the instruments have to be worked by themselves. So there are a lot of things we need to plan ahead. So we need to have a schedule to tell the telescope what to do and control the telescope and the camera, and also to take the images. And there are a lot of images to store, to be saved on site. We have a big disk array, and we have the real-time pipeline to reduce the data because the images are too big to transfer back by the satellite, and it's very expensive. So we store all the images there, but we have a pipeline to reduce the data and to get the results back. So this is the the small cut of the images we took back. So we can find some transient candidate. We can find some variable sources and only get those sources back. And if there's any problems, the computer will send back an alarm to our cell phone. So we know we need to connect to DOMA and to check what's wrong and what's going on. So usually if everything's fine, we don't have to touch it. So it's going to, the telescope will work all by itself automatically. So that part is basically the astronomical research. I'm not going to talk about cover all the details because I know people don't have much background in astronomy. So I'm just trying to tell you what we have been doing there. So another big part is site testing. So we try to prove that site is the best. So this one is for the sub-millimeter band. It's also called terahertz. We have different instruments, and we finally got the result. So this one shows how good the transmission is. That means how much the signal can go through the atmosphere and we can receive it on the ground. So that's a comparison for many sites. So Mauna Kea, the red one, is from Hawaii. Atacama is in northern Chile. It's so far it's the best site for the sub-millimeter observation, and they already have that ARMA array. That's a telescope in radio. But talking about the condition, the observing condition, Dome A is still better than Atacama because it's drier. It's extremely dry. So if we can build the similar instrument at Dome A, then it will be more efficient than ARMA at Atacama. So that's for the sub-millimeter band. But in the physical band, it's more complicated. There are many parameters we need to consider. So the first thing is we need a very dark sky. So we measure the sky darkness. So it needs to be low sky brightness. So these are the magnitudes in when we measure the sky. So the larger the number, the better. So when the number is larger, that means the sky is very dark. So we compare to some other observatories. So this is the largest number, which means Dome has the darkest sky. So it's good. And we also have another instrument getting the similar results. So it's like in the different bands, these are the visible color. So in those colors, the sky background is compared to the best site in Hawaii or northern Chile. So that's just one thing. We need to know more about the site. So we built some other instruments to try to get the data to quantify the merits of this site to be a good astronomical site. So I will talk about them one by one. So the first one is actually an all-sky camera. So that's an image we took. So we look at the whole sky and took images. We want to know how clear it is and whether the aurora can affect our observation. So the result is very good. So it's clear 83% of the time. In ARMA, in Paranal, in northern Chile, so that number is like 70 or 72%, something like that. Okay, so you can also notice there are a lot of aurora. Those are not good for astronomy to see bright in the sky. But the things like we can solve that problem because those aurora lines are very narrow lines in the spectrum. So you can use customized filter to block them so they don't affect our observation. Okay, so this is another way to show our data. So all the blue color are the good clear nights, clear time. So when it gets to when Antarctica gets dark, the dark time increases from April to June, and then we have the polar night, a 24-hour night. And then it gets less when it goes to Antarctic summer. So, but anyway, so the clear rate is very high. It's 83%. So I mentioned the thing, the star twinkling. So we also need to measure that part. So that's related to atmosphere. So usually when you talk about atmosphere, there are different layers, many layers. But in Antarctica, we can simplify that. We can only leave 2 layers. So on the ground, near the ground, there's turbulence. There's a turbulence, and we call that atmospheric boundary layer. In that layer, the atmosphere is not stable. There are a lot of turbulence. So the thing is not good. But if you go above that layer, when you get to free atmosphere, the atmosphere is very stable. And we are supposed to have very good thing. So we are doing this work in Antarctica. So we have this instrument to measure the thickness of the ABL, the atmosphere boundary layer. And it shows that the median value is very low. It's only 14 meters. That means if you build something above 14 meters, you get to the free atmosphere. And then you have the very good thing, very stable atmosphere. So we also compared that to another site in Antarctica. It's called Dome C. So at Dome A, it's 14 meters. At Dome C, it's 30 meters. So it's easier to build something at Dome A. In a temperate site like Paranal or Hawaii, the ABL is usually over 100 meters. So you cannot build something like 100 meters or several hundred meters tall to avoid the boundary layer. Okay. And also we have this instrument. This is actually a weather station, but it's not for meteorology. It's for us, for astronomy. So we built this like 15-meter tall, and we have the sensors at different heights. So what it measures is like the different temperatures, the temperatures at different heights. And we can see it's also divided by layers. They don't mix up. And also another thing is the temperature goes up with the height. So the temperature is lower on the ground and it's higher on the when you go higher. So that way is very stable, not like here. So here the temperature, the air temperature is hot on the ground, close to ground, and when you go up, it's getting colder. Then there will be convection, so and there will be turbulence. But in Antarctica, the cold air is here, the warm air is here, so there's no convection. The cold air is here because the ground is ice, very cold. Yeah, so we call that temperature inversion. If that happens, the air, the atmosphere is very stable. So that's why we found the reason why the atmosphere is stable in Antarctica. Okay, so when it's stable, it implies very good thing, but we need to measure the thing, and we need to know the numbers. Okay, so we built this instrument. Because we need to work to put the instrument in Antarctica, we test it in a very cold chamber down to minus 70 degrees and make sure it works. We also take it to a high altitude plateau to test if it's working. So that's basically the principle of how we measure the thing. So we take images of the stars. They are moving. The moving of the stars corresponds to the turbulence in the atmosphere. So we can measure the turbulence directly from their moving. So then we can calculate the thing. So that's the basic principles. So we built the telescope, we built the instrument, we set it up in Antarctica on this tower. This tower is 8 meters tall. And you can see those two small telescopes, not very big, like this size. So these telescopes are specifically for this measurement, not for astronomy observations. And here's the result. So we got all the data. So this is a histogram. This can be divided into 3 components. So when the boundary layer is below my telescope, we can measure the free atmosphere. And we got the free atmosphere thing here. So when the boundary layer goes up, sometimes it's tall, it covers this height. Then we get the turbulence. The thing is not very good. So the thing is like 2 arcseconds. So for the boundary, for the atmosphere, for the free atmosphere thing, it's only 0.3 arcsecond. And for northern Chile and Hawaii, that number is 0.6, 0.7. So you can already tell this is better than the current best observatories. And also at 8 meters, we have about 30% of the time we can get this free atmosphere thing. And we also get some best thing. It's very, very small. It's only 0.1 arcsecond. So it's comparable to the space. In the space, there's nothing, 0, but we are getting 0. So sometimes we call this place a subspace site, a subspace place. We have done this for 3 years. So we have data for 3 years. When you look at the histogram, the distribution are very similar. So the first column is the most important. That's a free atmosphere thing. So they're basically around 0.3, less than 0.4 arcsecond. And you may want to know that how we can get most of the free atmosphere thing without worry about the bad thing. So if we want to do that, we need to have a higher power. So if we have a higher power, we can get above the boundary layer more times. Then we can get more free atmosphere thing. This is actually already observed at Dome C. At Dome C, they have instruments at different heights. So at 8 meters, you can see there are a lot of bad things, not very much good ones. But when they raise the instrument to 20 meters, so the bad thing, the number of the bad thing points is smaller, and they get more and more good thing, the free atmosphere thing. So we have this solution if we want to have more time of the good thing. And another thing is we want to compare Dome C and Dome A. So at Dome C, at 20 meters, is comparable to Dome A at 8 meters. That's again, what I mentioned, we can do things much easier at Dome A than at Dome C. Okay. So here's the summary. So we have proved that Dome A has the best observing conditions for astronomy. It's not just optical, infrared, and terahertz sub-millimeter. We expect it in the long wave radio and the neutrino and many other regimes. They also have the best conditions, but we also need to test that to measure that. One thing I need to caution is the best observing conditions. What I mentioned does not equal to the best observatory. Because if you want to develop that into an observatory, you need the logistics support. You need to build buildings, build telescopes. And we can easily tell that it's much harder to do that at Dome A than in northern Chile, right? So we still cannot call Dome A the best observatory. So, but northern Chile and Hawaii still have the best observatories now. Okay, I'll stop here. Thank you.
Thank you so much, Dr. Chan, for your presentation. Thank you for visiting us and show advanced result in statistics in Antarctica. Thank you so much. Let's go to the
Questions.
question of the ¿alguien tiene alguna consulta del público?
I have a question about ASP3.
Okay.
Have you measured the PSF size?
Yeah. Yeah. This one. I didn't put the results here. Yeah. So we have problems with this telescope. So it's not very tall. It's only 4 meters. So it doesn't reach the free atmosphere very much. Sometimes, but not many times. So when it reaches the free atmosphere, the PSF is very narrow. It's like 1 arcsecond, because also the optical design. But this telescope had problems because there's the tube thing, the thing inside of the telescope is big. We have the camera inside. So we have the camera inside the tube, and the heat dissipation is not very efficient. So it causes a lot of tube thin. So the actual full width half maximum is like 4 arcseconds. Not very good.
More question? More question?
You first. Okay. Do you notice the problems with the Starlink satellites or the lower orbit satellites?
I mean the problem or or for communication?
Contamination of the images.
Okay. Yeah. Yeah. We realize that, and that's the problem for all astronomers all over the world. People have calculated how much that can affect our observations. There's a big project called LSST in Chile. So they have did all the simulation, and I forgot the conclusion. It's like maybe a few % of the images will be affected by that. So that's really unfortunate, but we cannot do anything about it. But on the other hand, Starlink is very good for us when we do work in Antarctica for the satellite communication. It's a very good tool. Yeah.
Yes, in the audience, we have a lot of engineering students, undergraduates. And what can you tell them if some of them are interested in developing instruments or participating in this kind of projects, either maybe not Antarctica, but maybe in the north of Chile? What would you recommend students if they're interested?
Okay. Yeah. So I'm an astronomer, but I'm doing some engineering right now because if you need some specific data or instrument, nobody else is going to build that for you. So you have to build that by yourself. But you all have the engineering background. That's very good. And we have a lot of engineering work for the astronomy, not just for Antarctica, but also for the northern Chile, those observatories. They are building the largest telescopes in the world, like 30 meters, 39 meters aperture. And they need a lot of engineers, a lot of work. So maybe you need to pay attention to what they are doing, understand, learn about what they need. So then you will have a goal, and you know, if you want to work with them or if you are interested in that, you know what else besides your classes, besides your own homework, you need to know what else you need to learn to understand. Then maybe when you graduate, you can get a job with them. Yeah.
Maybe the last question, and similar than Ricardo, is about the STP device. You need some support for electrical engineer for install the STP in the north of Chile.
Okay, yeah, Jaime is talking about the instrument we are collaborating to build. So that's actually not astronomy. It's basically just the electrical engineering. So we use a photodiode to observe the tiny change of the light from the moon. So then we can calculate how the turbulence, how much the turbulence is. So it's basically just the electrical engineering. So I think most people in your department can do better than we do. Yeah. We may need some help when we deploy that instrument to northern Chile. So then we can talk about that.
Ok, entonces muchas gracias por la asistencia. Vamos a darle el último agradecimiento al profesor Chan. Bueno, Priscila, en este caso nos va a traer un pequeño regalito. This is like a souvenir for you.
Oh, okay.
From the
Thank you.
team and the department. Okay. Yeah, you wanna solo. Gracias por asistir. Hasta luego.